Objective 4. Compute and interpret probabilities using the classical method. Now, the empirical method gives an approximate probability of an event by conducting a probability experiment, whereas the classical method of computing the probabilities does not require that a probability experiment actually be performed. Rather, it relies on counting techniques. The classical method of computing probabilities requires equally likely outcomes. An experiment has equally likely outcomes when each outcome has the same probability of occurring. For example, when a fair die is thrown once, each of the 6 outcomes in a sample space 1, 2, 3, 4, 5, 6 has an equal chance of occurring. Contrast the situation with a loaded die in which a 5 or 6 is twice as likely to occur as 1, 2, 3, or 4. Now, when computing probability using the classical method, now, if an experiment has lowercase n equally likely outcomes, and if the number of ways that an event E can occur is lowercase m, then the probability of event E, meaning the probability of event E occurring, is the following. We're going to say that the number of ways that E can occur, which would be m, divided by the number of possible outcomes, lowercase n. So if S is the sample space of this experiment, then we would say the probability of event E occurring is equal to the number of ways that event E can occur divided by the number of possible outcomes, where n of E is the number of outcomes in E, and n of S is the number of outcomes in the sample space. Okay, now let's take a look at an example. It says, computing probabilities using the classical approach. Now, a pair of fair die is rolled. Fair die are die where each outcome is equally likely. So the possible outcomes of this experiment are shown in the figure. Here's the first one. It's a pair of die, right? So if we know that that's a pair of die, that means that we have the following. Here is one roll. Here is another roll. Okay, so we want to compute the probability of rolling a 7. Okay, well, first and foremost, to compute probabilities, okay, using the classical method, we count the number of outcomes in the sample space and then count the number of ways the event can occur, and then divide by the number of outcomes by the number of ways an event can occur. Okay, so there are 36 equally likely outcomes in the sample space as shown in figure 1. So we can say that n of S is going to equal 36. So remember, in this example, we have a pair of fair dice. So that we have one, okay, just so that we know here, we have 1, 2, 3, 4, 5, and then 6. And if you look at the amount of rows in here, we have 6. So therefore, that 6 times 6 is going to give us 36. So that is telling us the following. That is telling us that there are 36 equally likely outcomes in the sample space as shown in the figure, so n of S is equal to 36. Okay, next, the event E is asking us of rolling a 7. So event E is to compute the probability of rolling a 7. So we're going to let the event E equal rolling a 7. Okay? So, how do we know about the 6 outcomes where it's rolling a 7? Well, let's take a look here. Okay, where do we have where it rolls a 7? Well, here's 1. There's 2. There's 3. there's 4, there's 5, and then there's 6. So remember, the first one is 1 and 6, and then 2 and 5, 3 and 4, 4 and 3, 5 and 2, and 6 and 1. That has 6 outcomes. So therefore, n of e is equal to 6. So now what are we going to do? Well, we're going to use our formula. Our formula tells us that the probability of event E occurring, which is equal to P, which is equal to roll a 7, is going to equal the following. We have n of E, which is the numerator, which we found was 6. And then we found that n of s was 36. So 6 divided by 6 is 1 over 6. So the probability of rolling a 7 is 1 out of 6. Okay, next it says compute the probability of rolling snake eyes. That is, compute the probability of rolling a 2. Okay, so what are we going to have to do here? Well, to compute the probabilities using the classical method, we have to count the number of outcomes in a sample space and count the number of ways the event can occur, and then divide the number of outcomes by the number of ways the event can occur. Well, first thing is first, we know that the event F is to roll a 2. So the event F, okay, is compute the probability of rolling a 2. So how many times can we roll a 2? Well, if we look here, we have 1 here, that's 1 and 1. And are there any other scenarios that show a 1 and 1? It does not. So therefore, we have 1 and 1, so it has one outcome. So we're going to say n of f is going to equal 1. Okay, now what we need to do is now we're going to use our formula to find our result. Okay, so to find our result, we know that the probability of f occurring is to roll a 2. Well, n of f is equal to 1. And we know that the total amount of the outcomes that are in the sample space is 36. So therefore, we have the following. We have 1 over 36. So the probability of rolling a 2 is 1 out of 36. Okay, in part C, we're going to comment on the likelihood of rolling a 7 versus rolling a 2. So what we're going to do is we are comparing. So we're saying that because P of roll a 7 was 6 out of 36, and because P of roll a 2 is 1 out of 36, rolling a 7 is 6 times as likely as rolling a 2. In other words, in 36 rolls of the dice, we expect to observe about 6 7s and only 1 2.